Professor Dave and Chegg here. We are now able to draw Lewis structures for any molecule, which tell us a lot about the structure of a molecule. They tell us which atoms are bonded with which other atoms, whether by single, double, or triple bonds, as well as any lone pairs that may be present. But they have one limitation. They are two-dimensional representations of molecules that in actuality are three-dimensional objects. We need a way to describe the three-dimensional structure of molecules. This includes the angles between the bonds as well as the spatial orientation of all the atoms. The model we will use to determine these things is called valence shell electron pair repulsion theory, or VSEPR theory for short. This will be a very important topic, so let's go over this theory now.
The central idea of VSEPR theory is that the things that surround an atom, whether they are bonding pairs of electrons or lone pairs, consist of negatively charged electron density, and these areas of electron density will repel each other. This means that the electron domains surrounding an atom will spread out to be as far away from each other as possible. The orientation that these electron domains will adopt depends on the number of them present. Two electron domains that surround a central atom will find that a 180-degree bond angle is the best way to maximize the distance between them. This will be called a linear electron domain geometry, and we will call the central atom sp hybridized because it needs to hybridize one s orbital and one p orbital in order to make the two sp hybrid orbitals to accommodate this bonding pattern. We will explain this hybridization process in a little more detail in an upcoming tutorial. For now, just try to internalize the number of electron domains and correlate it with the number of orbitals that hybridize. For 3 electron domains, 120-degree bond angles would be adopted. This is a trigonal planar electron domain geometry. Here, the central atom is sp2 hybridized, requiring one s orbital and two p orbitals to hybridize to generate the necessary hybrid orbitals. With 4 electron domains, we must begin to utilize a third spatial dimension, so it won't be 90-degree bond angles. If 4 domains adopt a tetrahedral geometry, there will be 109.5-degree bond angles, which is substantially larger than 90. Here, the central atom is sp3 hybridized, using all the s and p orbitals in its valence shell to form the necessary hybrid orbitals. For 5 electron domains, we get the trigonal bipyramidal geometry, which has both 90-degree and 120-degree bond angles. This requires accessing d orbitals to expand the octet, so the central atom is sp3d hybridized. And for 6 electron domains, we get something called an octahedral geometry, with all 90-degree angles. Here, the central atom is sp3d2 hybridized. Once again, each of these geometries is adopted because it allows for the electron domains to spread out in space as much as physically possible while remaining bound to some central atom. And the number of electron domains determines the number of atomic orbitals that must hybridize to generate the necessary hybrid orbitals to accommodate the bonding. This table summarizes the geometries that are dictated by the number of electron domains that surround a central atom, which correspond to a particular hybridization. But these larger categories can be split up into subcategories if some of the electron domains are lone pairs rather than bonding pairs. This will allow us to make the distinction between electron domain geometry and molecular shape. This describes the placement of only the atoms rather than both atoms and lone pairs. If a molecule has no lone pairs, such as with methane, then the electron domain geometry and the molecular shape will be the same, since all of the electron pairs are covalent bonds that lead to other atoms. We know that this molecule will be sp3 hybridized and therefore tetrahedral, and the way we represent this three-dimensional molecule in 2 dimensions is either with a ball and stick model or with dash and wedge bonds. When we use this notation, the wedge bond implies that the atom is coming towards you or is closer to you than the plane of the screen, and the dashed bond implies that the atom is going away from you or is farther away than the screen. If we look at other molecules that have tetrahedral electron pair geometry, we can see that the molecular shape will begin to change as we replace atoms with lone pairs, because the molecular shape is only concerned with the locations of atoms, not lone pairs. Look at ammonia, for example. Nitrogen has 3 bonds to hydrogen atoms and 1 lone pair. That's 4 electron domains, so ammonia is sp3 hybridized and therefore has tetrahedral electron pair geometry. But the lone pair is not included in the molecular shape. We give this molecule a different name when it comes to the molecular shape. We will call it trigonal pyramidal. Let's compare methane and ammonia in order to see that there are similarities in the orientation, as they have similar bond angles, although with ammonia they contract slightly due to the additional repulsion offered by the lone pair, but they certainly have different shapes because of the differing numbers of atoms. We could do the same for a water molecule, which has 2 bonds and 2 lone pairs around the central atom. That means it has 4 electron domains and will be sp3 hybridized, with tetrahedral electron pair geometry. But with 2 lone pairs, we will call the molecular shape bent. The bond angles decrease even more as a second lone pair is added, again because lone pairs repel other electron density slightly more than bonding pairs, and we should take note of these angles for methane, ammonia, and water. This table will show us all of the molecular structures that are possible within a particular electron pair geometry as we successively replace atoms with lone pairs. The more electron domains there are, the more possible molecular structures there are, because there are more combinations of atoms and lone pairs possible. We should also note that for most geometries, each position is identical, but for trigonal bipyramidal compounds, there will be axial and equatorial positions that are not the same, given the combination of 90-degree and 120-degree bond angles, sort of like a trigonal planar geometry and linear geometry combined. In this particular geometry, lone pairs will tend to occupy equatorial positions. With all the categories understood, let's go over a general algorithm for assigning electron domain geometry and molecular shape to any covalent compound. First, we must write the Lewis structure of the molecule or polyatomic ion. Next, we must count the electron domains surrounding the central atom. Each single bond, double bond, triple bond, and lone pair counts as one electron domain. Next, the number of electron domains corresponds with a particular hybridization and electron pair geometry. 2 is sp hybridized and linear. 3 is sp2 hybridized and trigonal planar. 4 is sp3 hybridized and tetrahedral. 5 is sp3d hybridized and trigonal bipyramidal. And 6 is sp3d2 hybridized and octahedral. Lastly, we use the number of lone pairs to determine the molecular shape, which will be a category within a particular electron pair geometry. If there are multiple options for how to distribute lone pairs, we must do so in the way that will place them as far away from each other as possible, such as placing them in equatorial positions for trigonal bipyramidal geometry, or opposite each other in octahedral geometry. Let's try a few examples: CO2, BCl3, and SF4. First, we must draw the Lewis structure for each molecule. Those will look like this. Now let's count up the electron domains. The carbon atom has 2 electron domains. That's the 2 oxygen atoms. The boron atom has 3 electron domains, the 3 chlorine atoms. And the sulfur atom has 5. That's the 4 fluorine atoms and the lone pair, which must go in an equatorial position. We must be able to draw the correct Lewis structures in order to have the correct number of electron domains, so make sure you are comfortable with this first. Next, let's assign the correct electron pair geometry on the basis of the number of electron domains. That will be linear, trigonal planar, and trigonal bipyramidal, respectively. Lastly, the molecular shape will be different for any molecule that has lone pairs on the central atom. SF4 is the only one that does, so let's look at that one. With 1 lone pair, which we would place in an equatorial position, we will say that this molecule has a seesaw molecular structure.
So to review, assigning geometries is as easy as drawing the Lewis structure, counting up the electron domains to assign the hybridization and therefore the electron pair geometry, and if there are any lone pairs on the central atom, assigning it a different molecular shape. And that covers the basics regarding VSEPR theory. Professor Dave for Chegg. See you next time.